Demotivational poster for the day. Triumph. The greater the accomplishment, the more likely people aren't going to believe you did it. Very true. We're talking about springs today. There's many different types of springs. The ones you probably think of that come to mind immediately when I say the word spring is either the season or it's helical coil springs. Those are the ones people usually think about. Of course, you compress either end of it, and the amount of force required to compress it more increases, right? It's proportional. The amount of force required is proportional to the amount of compression. But there are many other types of springs. You may have seen torsion springs, and there's many configurations of all these springs. If you think about a garage door, for example, most garage doors these days are counterbalanced not with linear extension helical coil springs, but with torsion springs. And those springs aren't just a few wraps of spring or a few coils, as they're called. Rather, they are, I think it's about 50 to 100 coils, if I remember right. I installed my own garage door of used parts because there was a place I found that they installed garage doors and they just basically threw out all the old parts, and I asked if I could sift through them and reuse some or take some, and they said sure. So I found plenty of parts and plenty of good parts, so I installed my own torsion springs, and those things are pretty dangerous. They're very thick springs. Turns out there's actually a sort of a four-pointed connection point on the end of each spring, and you can put a long lever in this connection point and turn the spring tensioning it. And of course you've got to move one down, then get the next bar in the next position, move it down, and so forth. I mean, if the thing lets go and you hit yourself in the head, it could kill you. It can be quite dangerous. But I'm still alive. I didn't get hurt by it. I was very careful and installed my own torsion springs. But you have to pre-tension them, because as the garage door rises, you want the springs to take more and more weight off, essentially, or basically counterbalance the door. You can't start from zero. Basically, the spring can't be in what it's called its free state. So many different varieties on all of these springs. For example, there are extension springs. What's shown here is a compression helical coil spring, but there are extension helical coil springs. There are flat springs. Flat springs you've probably not seen. You may think of leaf springs when you think of flat springs, and they are related to each other. They're just basically flat stock that have been bent. But the difference is that a leaf spring is a straddle thing, right? It's got connection points on either end, whereas a flat spring is simply a cantilevered beam. There are Belleville Springs. We'll see more about all these in the subsequent slides. And there's also constant force springs. A constant force spring is very different from the other types, because in a constant force spring, as you pull material off of the coil, the amount of force required to deflect it farther remains the same. So it's a constant force, thus the name. It doesn't matter how much you've pulled off of the roll, the amount of force to pull the next bit off is the same. Now, flat springs are interesting because if it's a simple cantilevered beam, then of course you can analyze that, but you can change the linearity or non-linearity of the beam by changing the cross-section shape. So that's something that is a way to tune the spring and make it behave the way you want it to. Often springs are assumed to be linear, but many of these actually don't behave linearly. As a matter of fact, real springs don't behave linearly, but we approximate most of them that way. And when you get into springs that are not, the analysis and design becomes much more complicated. Now here's an example. It's a leaf spring, and a leaf spring is kind of like a cantilevered spring, except it's mirrored on either side. And the nice thing about this is that it can reduce the stress in the spring, but you can also tailor the spring by adding different leafs of different lengths, and thereby change the deflection versus force characteristics of the spring. And that's what springs are all about, is deflection versus force. There are Belleville Springs, as I mentioned. These are basically washers that are bent that you can put back to back or cup to cup. There's even a calculator available for this type of spring. I've included a link here. If you download the presentation and click on the image on the right, that calculator, it'll take you to a website where I found an Excel spreadsheet that allows you to calculate things like the spring constant for the single spring and so forth, depending on how you stack them and arrange them. Now, the interesting thing about these is that you can create very large loads with very small deflections. And now they are typically nonlinear. These are typically highly nonlinear, but they're commonly used as a locking element around bolts, nuts, things like that. Because as you back off the nut of the bolt, there's still significant force applied to the the nut or bolt, whatever it is, or screw even. Here's an example from my childhood. My father used to have a flashlight like this. I'm the proud owner of it now, or I'm not sure if I should say proud owner or trying to keep the darn thing working. But it's a wind-up flashlight. And when I was a kid, he always liked going in caves, so I've been in probably every cave in this, within probably 100-mile radius of home. And I've seen some interesting things. You probably know of stalactites and stalagmites, the things that grow from the, or really are deposited from the ground up or from the ceiling down. But you may never have seen a helictite except in pictures, which is where the growth comes down and then turns. Really interesting. I saw several of those in a couple of different caves. Anyway, so this type of spring, or this type of flashlight, he really liked because he always thought, you know, what if I get stuck in the cave and my battery runs out? And he liked the fact that you could wind this up and, hey, you've got more light. You can find your way out of the cave, hopefully. Of course, it's also possible to find your way deeper into the cave with a light, thinking you know where you're going. But anyway, so he always liked this type, and he had several of these, well, actually different types of these when I was growing up as a kid. But this was an interesting one because the spring is a constant force spring, and I've pointed to it with an arrow, but what you can't see is on the other side there's a handle. In fact, you know what? I've got one right here. I'll go ahead and show them to you on camera. It's a little dirty, but there's one. There's a handle on the other side, and it opens up and you can wind the spring. And what happens is you're just winding the spring from this reel to this reel, and that puts energy into the system, and then you can turn it on. Now this one's not working right now, or I'd flip the switch and let you see that it works. This company also made another one that was clear, and of course he bought the clear ones because he likes to see how things work. But it's got a handle on it, but this is a radio instead. I believe the company's still in business, but they're making smaller units of these, and they're still, you know, mechanical energy storage where you can charge them up, and they're good for emergencies, I suppose, if they operate. But it's a constant force spring, so as you're cranking that handle, it's not like it gets harder and harder. It's still the same amount of work per revolution because the spring is the same force to, you know, move it another inch as it was the last inch. This is examples of some springs in industrial designs from Professor Dew's experience. And the springs, there's actually two types you can see here. There are metal springs. You see those as the coils, the compression springs. There's at least 4 in this view, well, at least 3 in this view, probably 4. But there's actually another type of spring. The interesting thing about springs is you can classify them in a way based on how reversible they are. That's a term from thermodynamics, and what it really is talking about is, do you get out of it as much as you put into it? Okay, so if I take a metal spring and I compress it and I plot force versus position, it turns out that I'll actually have to apply a little more force as I compress the spring than I get back as I expand the spring. That's because some of the energy that goes into the spring does some things like warming up the spring material, or maybe a few bonds have been broken, or you know, maybe some grain boundaries have been moved within the spring. But some of the energy is lost. Now there are even more lossy springs, and these are simply things made of rubber. So you can see a couple of what would really be considered shock absorbers here. And what they do is that as you stretch rubber, you're putting energy into it, but when it reforms, or what's the right word? Well, when it goes back to its original shape, goes back to its free length, it doesn't pull back with near as much force, and you don't get as much work out of it, force times distance, as you had to put into it. Now this can be good because these things act to dampen out oscillations. So the black rubber thing you see there that has writing on it, and you can tell there's another one in the shadow on the right of the picture at the bottom. Those I would still consider a type of spring, but they're a very lossy spring. And of course these also behave very non-linearly. Here's some more large springs. You can tell these are fairly hefty things because of the wire diameter, and we've seen several different coil spacings. The last one had mechanical springs that were of course made of steel that had very large coil clearance or coil spacing. This one's much smaller, and you can tell some idea about how much weight each of these machines must be, because we're talking about very large diameter wire that's used to make the springs. Here's another example where the springs are just isolation dampers, so very lossy springs, and you can see them better here. The 4 rubber, well, you see 3, there must be a 4th on the other side. Here's an example of leaf springs where the springs are literally cantilevered. Now you can't tell it exactly, but they are in fact cantilevered where you see the loose bolt there. You see one end of the spring is clamped down so that it cannot rotate back at the base, but the other end can rotate around, and so it is allowed to rotate around that fixed point. The whole spring deflects like a beam, and it's connected to the other end, but it's allowed to pivot at the other end. So these are leaf springs. Now what about the physics behind it? Well, you've probably seen force versus deflection for quite a while now because you've had physics classes, and we usually assume that the force is proportional to the displacement of the spring from its free length. But that's assuming a linear spring. Now for this class and for this chapter we will assume linear springs, even though many springs are actually quite nonlinear. Now if you have springs that are in parallel with each other, now what does that mean? Well, that means that they are side by side. Well, then this effective spring constant of all those springs together simply is the sum of all of the individual spring constants. So you end up with a higher stiffness. In other words, it takes more force for the same deflection if all the springs are side by side and resisting the force. Now if you've ever gone to an amusement park, they've probably tried to get you to ride on the slingshot type rides, and those rides are interesting to look at because they have a box of springs usually off to the side, and they're usually extension springs, and what you'll notice is either the upper or lower platform will move. A lot of times one end of the springs, I think it's usually the upper, or is it the lower? I don't remember. Anyway, let's say it's the lower. What will happen is a motor will move the lower plate down that has a bunch of springs attached to it, all in parallel, and stretch the springs, putting energy into the springs. And then, once the ride is ready to go and the springs are released, the upper plate actually moves down and pulls on the cables very hard so that the slingshot capsule goes up in the air. Of course, you can find all kinds of interesting videos on YouTube of people passing out on these things. I've never ridden one. I'm a little bit scared of it. I like most rides, but that one kind of freaks me out. What really freaks me out is the fact that I've paid, $20, $30, $40, $50 to get into the park, and they want another $20 or $30 to ride this thing. So forget it. I've never ridden one. I probably never will. If springs are in series, so if they're tied end to end, then the effective spring constant is reduced. To calculate the effective spring constant, you take 1 over the equivalent or effective spring constant, and it's equal to 1 over it's the sum of the inverses of all the spring constants. You can see the equation there. So you can of course solve for the equivalent spring constant, and it's lower than any of the individual spring constants. Coil springs are very common. As I said, that's one type that you probably thought of. We'll talk a little bit about these because we're going to design some of these coil springs. The end treatment on coil springs is a very important consideration. A plain spring without any end treatment where you've just cut off the ends, you can see that in figure A, plain ends, it's a right hand spring. So as you wrap your fingers in the direction of or you move them along the coils, your thumb points in the direction of motion. That one's to the left, well, the way I've oriented my hand, but it's following my right hand. You can see a left-handed spring on the right in C, because of course, wrap your fingers around the coils, your thumb points in the direction of advancement. But here we've got one end that has been so-called squared and ground. What does that mean? Well, the last coil has been closed, right? So that last coil was out, and it's been bent so that it's touching the adjacent coil, and the end has been ground off. Why would you do that? Well, if you've ever taken apart a ballpoint pen where you could click it to extract or pull back in the point, you've probably pulled it apart and grabbed the spring, and you started compressing the spring, and what happened? Well, the spring flew out the side. That's called buckling. And if the ends of the spring are flat, you can actually reduce the chance of buckling because you can basically apply more of a moment to the ends of the spring. Now, in this case, we only have one end that is squared and ground, but of course you can have both ends squared and ground. Sometimes you don't bother closing the coil, rather you simply grind the end off, and you can see that in D. On the other hand, you don't have to grind, you can simply close the coil. So you can take the last coil and close it so that the last coil is touching and not really an active portion of the spring, and you can see that it's touching there but not ground in item C. Some terminology for coil springs that we need: when the spring has no force in it, we call that that length of the spring the free length. When it is installed, generally the spring will have some compression when it's installed, and that's called the installed length. And the image is not very good, so let me give you the symbols. L sub F is the free length, L sub I is the installed length, and that makes sense. They're just named free or installed. The operating position is typically not with the spring compressed all the way down as far as it can go where all coils are touching. That's actually called the solid length, and a lot of times you don't want to go to the solid length because the stress in the spring material will be too high. But that's the name of the length when all the coils are touching. But when the spring is at its most compressed design position, that's called the operating length, and the operating deflection then is the difference between the free length and the operating length. And of course the subscript would be, well, it'd be L sub O for operating, L sub S for solid, and this figure's in your book so you can look at it there too. Now the coil clearance, we usually define that to be the distance between the coils when the spring is at its operating position. So that's often, it's not shown here, but that's usually given the symbol CC for coil clearance. So that's an easy one also. Now the spring geometry, besides the length, involves the mean diameter, which is from center to center of the wire, the outer diameter, OD, and the inner diameter, ID. Don't worry too much about this table, just remember that it's here, and when we're working example problems, reference it to see where I get various equations from. Okay, so again, you can try to wrap your head around this right now if you want. It's not really all that worthwhile. Just look at this when you're working homework problems and when I'm working example problems with extension and compression springs. Finally, to talk about a design parameter, something we've just defined a bunch of symbols and what they mean in relation to the spring, but how do we get down to the root of the spring? How do we get down to its nature and its operation? Well, we're going to take the ratio of the mean diameter of the spring, remember that's from center to center of the wire, to the wire diameter itself. And usually we want this ratio to range anywhere from about 5 to about 12. And I've drawn in SolidWorks a spring that has a spring index. That's what this is called. Now be careful. This is not the spring rate. This is not K. It's not the spring constant. It's the spring index. It's something very different. It's a geometry ratio. Okay, so you can see a spring index or a spring that's drawn with a spring index of 5 and another one drawn with a spring index of 12. Now the reason you don't want to go below 5 is because the wire becomes really fat for the diameter you're wrapping it around. I mean, how do you think you start, or how do you think you make a spring? Well, you start with a piece of wire and you wind it around a mandrel, right? Basically a cylinder. You wind it around a cylinder. Okay, well, if you have a really thick wire and you really bend the heck out of it, it's kind of like a beam that you're bending and deflecting. Now remember, we are intentionally yielding the material. You don't want to bend it so far that you've strained it so much that you're near failure, right? That would be bad. And so a spring index of about 5 is about as low as you typically want to go. Now a spring index of 12, you end up with a spring that's very loose, right? That moves too much. As you compress it, it just has no real strength. And so any spring index less than 5 is hard to manufacture, and you end up with stress problems. Greater than 12, and you end up with a spring that's not very useful. Now, let's talk about what's going on with a helical spring. Now, I want to start this discussion with a small story about a vehicle I used to own. It was a Toyota pickup. It was a 1992 model, and they did some things a little differently in that pickup. It was really interesting. I ended up taking it up north when I was attending Purdue, and it kind of looked like this underneath the bottom. Now, I didn't have the four-wheel drive version, so I didn't have that front differential or anything. It was just the rear-wheel drive, cheap version. But they had a crossbar, and all of the salt and everything on the roads up north were a little more intense than down here near Louisville. And so that bar in the center almost completely rusted out, and I was really worried about it because that bar was made to hold one end of what's called a torsion bar. So just imagine a piece of wire, and if you take that wire and you torque it, it's going to resist it, right? It's going to develop some torsion. Well, in that vehicle, instead of having helical compression springs, they simply had a rod. And so these were called torsion springs, okay, or torsion bars. And what would happen is the A-arm that you see that's supporting the wheel, there was pre-tension in the rod, and so the A-arm was trying to go up, or no, the other way, trying to go down to support the weight of the vehicle, but the weight of the vehicle caused some twisting in that torsion bar. Now the end that was on the ground or on the frame of the truck the end you see here connected to that cross member, it had to be held very well, and so I was concerned that if this thing rusted out, it would let go of my springs, and basically the front end of my truck would be squatting. I guess then I'd have a lowrider, but the truck really didn't look like something that should be a lowrider. It was just a conservative truck, so it looked funny. So anyway, what happens when you stress a rod like that is you make shear stress. Remember, strength of materials and shear stress in torsional shafts and things. Now, basically, a helical spring is just like this. The only difference is we've taken that rod and we've wound it around a mandrel. So when you press the spring, when you compress it, you're really just twisting the rod. And so if you think of a small segment of a helical spring, what you're really doing is twisting it. That's really all it is. Now, because the geometry is a little bit different because it's been wound around a mandrel, it turns out that it's not quite that simple. Remember, in strength of materials, the shear stress was the same all the way around the outside edge of the wire, or the outside surface, the outer fiber. But in the case where a bar like this has been wrapped around a mandrel, the geometry is a little bit different. And so because of that, the stress profile is not quite the same all the way around the cross-section of the wire. As a matter of fact, the maximum stress on a helical spring that's been wound around a mandrel occurs on the inside diameter, or the inside surface of that spring. And so that's where you would expect failure to begin. Now here's our first equation to calculate stress in a helical spring, okay? So it's 8 kf dm over pi d sub w cubed. What the heck is all this stuff? Well, the 8 and pi have to do with strength of materials. Don't worry about where they come from. They're just constants anyway. F is the amount of force being applied along the axis of the spring to compress the spring, okay? K, that capital K, is called the wall correction factor. Now be really careful here. Most physics classes use it lowercase k for the spring rate, okay? We're not doing that. We've got two different K's here. There's uppercase K and lowercase k, and watch out for them because your author uses lowercase k sometimes for the spring rate. In fact, I think he uses it most of the time for this type of spring. This is just a correction factor for the fact that the spring is not just a simple bar, right? It's not just a rod. Rather, it's been wrapped around a mandrel and it has a different shape. So this corrects for that geometry so that this equation that basically comes from strength of materials applies and we get a more accurate value of the shear stress in the material. Now d sub m is the mean diameter of the spring and d sub w is the wire diameter. And so hopefully you notice that the spring index is in this, right? 1 dm over 1 dw would give us the spring index C, which also is in the wall correction factor, right? That's what that big C is. Now, of course, in the equation for the shear stress, we'd still have two wire diameters, so they'd still be squared in the denominator, but we could replace 1 dm and a dw with a C, a spring index. Now, there's many different materials that can be used for making springs, and you'll need to tab page 606, table 18.4, because this is where you'll find several different materials and their properties. Now, in springs, this is where we finally care about the difference in the elastic modulus between alloys. Now, steel has a modulus of about 30 times 10 to the 6 psi, 30 million psi. You may have that memorized by this point in your education. But in springs, that little bit of difference in the elastic modulus can make a relatively large difference in the spring, and so we include the effect of it. And you'll notice that for these spring materials, they've got the elastic modulus listed, and they do vary a little bit from one to the other. The allowable shear stresses for this type of spring are on page 602 through 604. There's a bunch of figures there. Be really careful with these figures. We're going to study springs that have torsional stress in them, so anything that's a helical shape, like a compression spring or an extension spring, we'll use these figures. So go to these figures, put a tab there because we're going to use them a lot, but make sure you write extension and compression springs only. Or maybe you want to put shear stress there because that's the kind of stress in that type of spring. When we talk about torsional springs, they can still be made in the same form, right? You still are wrapping a rod around a mandrel. But when you stress a torsion spring, it ends up being a bending stress because then it's more like a cantilevered beam. So be very careful. These figures on page 602 through 604 are not useful at all for torsion springs. These figures are only useful for extension and compression springs. And maybe that's what you want to put on that, is allowable stress for tension and compression springs. Okay, that's fine. However you want to note it, just be really careful because there's more figures on other pages that look a whole lot like this, and in the stress of an exam when you're using your book, you might flip to the wrong set of figures and get the answer wrong because of just choosing the wrong figures.